Okay, so in section 12.7, you learned about triple integrals, where you used rectangular coordinates, x, y, and z. Those are also called Cartesian coordinates, but we'll call them rectangular coordinates. You used rectangular coordinates to do your integration. But remember back in chapter 9, how many remember learning about cylindrical and spherical coordinates back in section 9.7? How many remember that? Robin remembers it, and Ryan and Jamal, good, and Diodath, and well, you know, why did you learn that? Well, it's going to be helpful for doing triple integrals. Sometimes, just like well, triple integrals. Sometimes you want to use cylindrical or spherical coordinates to do a triple integral. Okay. Now, of course, the question always is, you know, you have this triple integral over some solid. Okay, and then you have a function, okay, of x, y, and z. Okay, and then you have dv. Now, dv, again, in section 12.7, you're used to dz, dy, dx. Okay, or you could do, you know, dy, dz, dx, for instance. Okay, and there are 6 orders in which different orders, and one order is usually easier than the other, depending on how the solid is oriented. But now, if we're going to switch over from rectangular coordinates to cylindrical and spherical coordinates, that's going to change, you know, that's going to change what we have for x, y, and z, and it's going to change the dv as well. So dv, think of that as like delta v, a unit of volume. So for rectangular coordinates, a unit of volume was what delta z, delta y, and delta x, right? If you have a, you know, you have a you have like a cube, and I'm sorry it's not the most beautiful drawing, but you know, you have a cube here. Okay. Oh my gosh, I can't believe I cleared all that. All right, hang on. Let me do it again. They got to move that. They got to move that clear button way the heck somewhere else. You know what I mean? They got to do that. But maybe I'll talk to them about that. Sorry, it's not perfect. There we go. So, you know, you have a delta x, delta y, length of the base, length of the length, width, and height. Okay, so delta v is just delta z times delta y times delta x. And from there, you know, you get dv equals dz dy and dx. That's your unit volume. That's the unit that's your building block for your unit of volume, okay, with rectangular coordinates. But now what we want to do is see, okay, well, what would this be? What would dV be if you had cylindrical or spherical coordinates? So let's go ahead to cylindrical coordinates first. Are there any questions on this? Okay, let's go back to the book then. Okay, so let me see here. One moment, class. Make that a little bigger. Back to the book. Okay, cylindrical coordinates. So of course, cylindrical coordinates, you know how to plot a cylindrical coordinate in three-dimensional space. Cylindrical coordinates consist of coordinates r, which is a radius, theta, which is measured from the positive x-axis, and then z. Okay, and so if we were to think about what a unit of volume would be, a small unit of volume with respect to a volume element, they call it, in cylindrical coordinates, dV would equal, it turns out, r dz dr d theta. It's not just dz dr d theta. It's r times dz dr d theta. Now, why is that? Why is that? Because I always like to think in terms of base times height times base times width times height. Okay, and here the width is dr and the height's dz. But on the bottom there, and it's not, you understand, it's not an exact. It's not like a box, okay, but it's a volume element. But the r d theta is it's a length of an arc, a portion of a circumference. Okay, think of circumference. Circumference c equals 2 for a circle. Circumference is 2 pi r. So circumference of a circle is 2 pi r because a circle the arc is a distance of 2 pi. Okay, if I want to say this right, or if I'm not saying that right. The angle for a circle is 360 degrees, so hence 2 pi. So the circumference of a circle is 2 pi times the radius. Well, in this problem, d theta is your angle. It's your angle for this little blue volume element. So circumference or length of that little arc there is r d theta. So if you think about taking the length of that arc times dr times dz, okay, and think about the arc getting smaller and smaller, you're basically going to have base times width times height, where base is r d theta times width dr and height dz. That's how I mean, this is sort of how I like to think about it, and to justify why dv is r dc dr d theta. Are there any, without getting like real technical, that's how I like to think about it. Are there any questions on that? Okay, so then if we want to think about using polar coordinates, then your triple integral would have to be written in this format. The dv is r dz dr d theta. X, y, and z are replaced with r cosine theta. Well, x is equal to r cosine theta. Y equals r sine of theta, and z is z. And then you have if you're integrating with respect to z first, well, z is a function of r and theta. So you have two functions, u1 and u2, of r and theta, and then the radius r is when you integrate with respect to r, you have a bottom and a top function of h1 of theta, h2 of theta, and then the limits for theta are alpha and beta. Now this is going to be much easier when you see an example. So I'm going to go right to the example, but are there any questions in general on this? Okay, let's get right to the example here. I want to do a problem with cylindrical coordinates first. Okay, take a moment to copy this example down. Okay. All right, let me give you a moment or two to copy this example down from section 12.8. Okay, so we want to evaluate this triple integral. Now, do you think that I mean, right now, the way the triple integral is set up is we have integration with respect to rectangular coordinates. We're using rectangular coordinates. Okay. Do you think, this, by the way, is square root of x squared plus y squared, right? The whole thing. Do you think that rectangular coordinates is the best choice for integration here? Okay, right away I'm saying no on that. Christopher says no, Ryan says no. What makes you say that? You're correct. You're correct. What makes you why do you say that? Why would this maybe not work with well, Christopher notes that x squared plus y squared is of the form r squared. So we could maybe rewrite this integral in a little easier format. But why wouldn't what's kind of a could be an issue in terms of, you know, I mean, I can get the antiderivative of x squared plus y squared with respect to z would be the quantity x squared plus y squared times z, right? I could you know, integrate that. But where am I going to maybe run into a problem? Where might I run into a problem, class? I mean, we look at the limits. We look at our limits here. We look at our limits. And what would make integration difficult? Good, that's right, Robin. The square roots. The square roots could be a problem. And in fact, they are a problem. And even in, I'll tell you, even in MATLAB, I tried to integrate this exact integral with, you know, the rectangular coordinates, z, y, and x, and MATLAB wouldn't integrate it. I mean, it wouldn't give me an answer. It wouldn't give me a number, you know. I found that interesting, but nevertheless. Okay, so, all right. Well, now, let me ask you this. Based on the fact that we have these limits, can we draw the solid? Can we draw the solid of that we're, I mean, you know, we do have limits here. We have limits. So there must be a solid that goes with these limits here. Okay. Can we draw the solid E based on the limits? We can. We can. We certainly can, John. That's right. So let's go ahead and do that. Let's think for a moment. Now, let me see here. When I see here 2, since I'm integrating with respect to z, I think z equals 2. Z equals 2 is what? Z equals 2 is an equation of a what? It's a plane, a horizontal plane. Good, Ryan, good. All right, let's look at the bottom limit here. This limit is z equals plus square root of x squared plus y squared. Now, what's that going to be? This solid is bounded above by the plane z equals 2, and it's bounded below by this surface given by z equals square root of x squared plus y squared. What's that an equation of? That's right, John. It would be a cone. It would be a cone. And if you don't believe it, just square both sides of this, and you'll get z equals x squared plus y squared. Now we have to be a little careful because z equals x squared plus y squared is actually a cone, okay, that passes through the origin, but it has like a part below and a part above, right? Like an hourglass. But since we have z equals plus square root of x squared plus y squared, are we getting the top portion of the cone or the bottom portion of the cone? We're getting the top. Good. That's right, Robin. That's good, John. So what we have here is we have, in terms of our solid E, if we, you know, think about it in our mind, we have a bottom surface that's a cone, and it goes up until it hits a plane. Now, when the cone intersects the plane, what will it intersect in? What shape is the intersection of the cone and the plane? A circle. That's right. Good, Ryan. It has to be a circle, right? So now, in terms of the y limits, you have some functions here, top and bottom functions, that relate to a circle. Because if you have, for instance, y equals square root of 4 minus x squared, okay, well, you can square both sides and get y squared equals 4 minus x squared. Of course, this, okay, or you could write that as x squared plus y squared equals 4. Oh, that's a circle. That's a circle with radius 2, centered at the origin, right? But is this here a circle? Y equals plus square root of 4 minus x squared. Is it the full circle? No. Okay, is this here y equals plus square root of 4 minus x squared? Is it the top part of the circle or the bottom part of the circle? Top part of the circle. That's right, John. And then this here, y equals negative square root of 4 minus x squared, would be the bottom part of the circle. Okay, and then of course your x limits will go from -2 to 2 on that circle. So I'm just trying to sort of help you feel comfortable with what's going on here with these triple integrals. Okay, I'm trying to help. Is this helpful? This little discussion I'm having here, is this who's finding this helpful? Okay, wonderful, wonderful. Thank you, Robin. Thank you, John. Thank you, Eric. Good, good. So with multivariable calculus, we just have to be patient. You know, we know we can't just look at a problem and instantly be able to do it like in calculus 1, right? Because even then you had to think about it. But you know what I mean. It takes a little more time, you know, but we piece it together. All right, so on that note, let's go ahead to the solution here. We're not going to use rectangular coordinates here. We're going to use cylindrical coordinates. And so what I'm going to do, I have the integral rewritten here. We know it's difficult to integrate with rectangular coordinates. So we're going to convert the integral in terms of cylindrical coordinates. And I rewrote the solid E and the region D here. And then this would be the integral, triple integral, in cylindrical coordinates. Okay, so let me give you a moment to copy this down. Let me know if you have any questions, please. Okay. Okay, so of course, the x squared plus y squared is just equal to r squared. Okay, and that's how we got this r squared here. And then dv now is r dz dr d theta. Okay, so let's focus here then on the dz. So the cone is z equals square root of x squared plus y squared, but that would be just then the same as z equals r. So in terms of this line segment that I've drawn here, okay, this line segment right here, it's going in what direction? That line segment, that red line segment. What direction is the line segment going? What variable is that line segment going in? What direction? The z direction, up and down. Okay, so all right, what's then the, so it's going from a surface below to a surface above. What's the surface below? Z equals R, the cone, right? Okay, yep, Z equals R is my bottom limit when I do dz. Z equals R, and then it stops at what surface? It stops at what surface? Z equals 2, the plane. And so you see, that's how I get those limits. Now in regards to R and theta, here's R, here's theta. That just comes from my region D. Region D is if I take the cone and project it down into the XY plane, my region D is going to be a circle of radius 2. Okay, it's going to be a circle of radius 2. That's taking, again, that's taking, you know, the intersection, that circle, and projecting it down into the XY plane. So at that point, you know, all along here, along there, right, 2 is equal to the square root of x squared plus y squared, right? So that means 4 equals x squared plus y squared. And so 4 equals x squared plus y squared, then that's a circle of radius 2. So the radius goes from 0 to 2, and theta goes from 0 to 2 pi. Are there any questions? May I move to the next page? All right, Christopher's good. John's good. Okay, so now what we want to do is integrate this. We want to integrate this. Does this integral, I don't know why it's not, yeah. Is this integral here in cylindrical coordinates easier than the integral was in rectangular coordinates? Is it significantly easier? It is indeed. It is indeed. Okay, and so we're ready to integrate. So what I do then is I iterate the integral. So I'm going to, the integral of r cubed with respect to z is just r cubed z. I'm going to put in 2 and r in there, and that's going to get me 2r cubed minus r to the 4th. And at this stage here, it's now a double integral problem. And now you integrate with respect to r here. Your antiderivative will be r to the 4th over 2 minus r to the 5th over 5. You put in 2 and 0. Eight is the same as 40/5. And you get 8/5, and in the end you're going to get 16 pi over 5. Write that a little better there. Absolutely amazing. That's your integral I. So I let the triple integral equal I just because it's a little easier for me. All right, are there any questions at all? Ryan's good? Wonderful. It's absolutely amazing how math developed, you know. We always endeavor to try to get to find integrals, and these other coordinate systems help. And you know, in this case, the cylindrical coordinates helped us be able to solve the problem. I mean, if we can solve a problem, that's very valuable, right? If we have a way to solve a problem. Cylindrical coordinates provided the answer here. All right, let me stop the recording then.